Welcome back. In this video, we are going to work backwards. And I created this video because I think it's important to analyze what we just concluded and kind of make sense of the numbers to justify our answer. So I promise this video is a worthwhile one to watch. So in the last video, we did the example where we did a comprehensive design of a beam. And we chose a W12 by 19 beam. And I want to work backwards to see how strong a W19 beam is given our, or as compared to what we're actually loading, given the pounds per linear foot and the span of the beam. So a W12 by 19 beam, I took a screenshot of the website. A W12 by 19 beam has a plastic modulus of 24.7. So I'm curious as to how much moment a W12 by 19 could actually have supported. So we can work backwards to figure out what the nominal bending capacity of this beam is. So we know that the nominal bending capacity is the plastic section modulus multiplied by the yield stress. So if we multiply it by 50,000, 24.7 by 50,000 gives us 1,235,000 pound inches. Of course, we want pound feet, so I'm going to divide that by 12, and we have a nominal moment capacity of 102,916. That's the maximum moment that this could actually support. How much did we have given our beam? We only had 44,145. So we said that the best member to choose is a W12 by 19. That could handle way more than what we actually have. Why? Why is it so much different? To put it in a graphical sense, this is what it could handle. This is what the moment diagram could have handled. This is what the moment diagram actually is. So all this gap right here, this is actually where the beam has been over-designed. This is how much more we are able to have versus what we actually do have. So I have a question then. Why? Why is there so much of a difference? There's actually twice during the beam design process that we over-designed our members to be conservative. What were those two times? Pause the video and think for a second. When did we beef up our number to give us such a drastically different finished result? Okay, well, question number 2 is, although not done often, steel members are often not the same height throughout the entire span of the beam. Meaning, like at the supports, it'll be one height, and then in the middle, it'll be a different height. So should the member be stronger in the middle or near the supports to maximize efficiency? Those are our two questions. One, where are we making this number? Where are we beefing this up? Where are we being conservative? Where are we overestimating? And two, if we were to custom make a beam, would we want it to be smaller or less height in the middle or near the supports? Okay, here's your answer. The two times that we beef up the number, first is when we multiply it by the factor of safety. That's when we do 1.67 multiplied by our max moment. So that's a huge jump right there. The second time is when we choose a member containing a plastic section modulus higher than what was created. You're never going to get a member, well, I shouldn't say never, but you're often not going to get a member that's exactly the plastic section modulus required. You're almost always going to have it be a little bit higher. So that higher amount than what is required is considered an over-design. It's not a bad thing. That's why the actual moment capacity of the beam is higher than what's required. And for a simply supported beam, the maximum moment occurs in the middle of the span. Therefore, we need to only ensure that our beam can support more moment there. Let's go back to here for a second. If I had the member be a lot thinner at the ends, this 103,000 probably would have been like over here if it was smaller. And then if I had the middle be 103,000 support, it would kind of follow that curve. So if we were in school, I would have had a really cool lab that showed this, where we actually go to the commons and we analyze the steel beams. And when you look at the steel beams in the commons, you'll find that one beam is about 35 feet or so, and near the supports, it's a pretty small depth. And then in the middle, it's so much bigger. And this is why. It's because the moment is bigger in the middle. And near the supports, the moment's not that big. So you don't need as much material there. So that way, with that custom built design beam, it would have this kind of curve to match what the moment diagram would be. And then finally, we didn't really touch on this too much, but not all beams are simply supported, meaning you have it on both ends. Sometimes you have like a balcony where it's free on one end and attached on the other. And the moment diagram for that one would be this. This would be the reactionary forces. If this is 20 kips going down overall, it's all being supported by this end, and then it goes to 0 because this can't resist the moment over here. So in cases where you have what we call a cantilevered beam, where you have a support only on one end, you want it to be thicker, the beam to be thicker near the support. And again, if we were in school, I would have taken you guys to the gym, because the gym has some of these type beam scenarios. And you'll see that near the support, the beam is super, super thick. And as you go further and further away, it's supporting less and less load. It gets smaller and smaller. So that just hopefully ties some things together. Again, the max shear occurs at the fixed end, as does the max moment. So that is what you would need. And that's it for beam design. So I believe we might next lesson or so work on more complicated scenarios, maybe like a simple building we'll design. I haven't decided yet, but that concludes the beam design videos.